Thanks so much for the opportunity to speak today about interoperability within the System of Environmental Economic Accounting, or SEEA. I'm excited to be here, and before I get started, I'll just add that while I'll be focusing on SEEA, the concepts and principles I'll be talking about today certainly apply to adjacent topics as well as many other broader scientific data and model integration challenges. So you've heard about interoperability all week. The definition I'll be using for today's talk is the ability of independently produced scientific content to work together with minimal effort. And the asterisk is here to remind us that when we talk about high-level interoperability, it's implied that we mean computational pipelines. So models and workflows need to support interoperability as well as data and data itself. I'll be using some definitions here from Heiler 1995 in talking about semantic and syntactic interoperability. In this case, syntactic interoperability implies compatible data formats and communication protocols, while semantic interoperability on the right means a data transfer where a receiving system can understand the meaning of exchanged data and reuse it appropriately. This is more complicated. It's an area that my colleagues and I have been working on for many years, and we think we have the basic tools and principles to be able to do it, and think that given the volume of science and the importance of the problem, that it's critical that we as a scientific community start to understand and coalesce around semantic interoperability. Why does this matter? In a nutshell, we need faster, better, and more integrative science. The status quo of science for years has been that we do a very painstaking set of work around the integration of often geospatial and other types of data around understanding and using the best scientific models. And this is a very slow process. At the end of the day, hopefully these data go into a data repository, but not always. Now, of course, cloud computing and cloud-based resources are changing this and have changed it quite a bit in recent years. But I think the status quo prevails, that there's still quite a bit of burden placed on the scientists to understand and manage all the data and models. And that just becomes less and less possible as the science continues to grow at the explosive rate that it has in recent years. So the world that we've been working toward and envisioning with semantic interoperability is underpinned by the semantic web. And in this case, we have a world where experts are contributing data and models and their knowledge of when and how to reuse them in a way that by design is interoperable and where a machine can combine and execute data and models at the request of users. This paradigm means that we can have a much more fast, responsive, timely, and ideally better and integrative set of science that gets done in response to user needs. Another way to look at this is that any individual modeler, no matter how expert, only has an understanding of a limited number of data sets and models. But there are quite a bit of other data and models out there that the modeler doesn't know about, may not understand, and which could be highly useful for their problem. If those data sets and models are available in a global knowledge commons, these could be used by the modeler. And even better, if the modeler is able to contribute their own data and models to that global commons, these two sets of data and models can interact and work together, and others can reuse these and have a better base to draw on for science for yet other distinct challenges. Of course, the main draw of semantic interoperability is the ability to do integration through machine-supported interoperability, producing automated maps, reports, and provenance. And then ideally, also the iterative updating of models as new data become available. That's the view from the perspective of an individual modeler. When we think about this at the country scale for something like SEEA, a country, when it's implementing SEEA, in my mind, goes through a circular process where they figure out which accounts they want to compile, they assess and assemble the available data and models. Skipping ahead to step 4 here, they test, publish, and validate accounts, and then they do periodic reassessments to integrate new data and models as they become available. If we have a global data and model commons, and countries are able to draw from that, they have a wider basis of science that they can use in compiling their accounts. And similarly, they can contribute to that global knowledge commons and improve it over time. Of course, there's more than just one country operating out in the world. So if we have that global interoperable knowledge commons, countries may make relatively even use of it and contributions to it. Some countries may draw from it more extensively. Other countries may contribute to it more extensively. But this elevates the ability of all countries to participate in ambitious global monitoring, and we believe is an important prerequisite to effective global implementation. Why does this matter? We want to do this more quickly. We want countries to be able to independently produce, use, and institutionalize ecosystem services and other knowledge. And their ability to do so is growing, but I would argue it's growing too slowly. We may be able to do it more quickly if, as the status quo improves and as better knowledge and tools become available. But I think with a coordinated global focus on interoperability, we can do this more quickly, and that's to everybody's interest in today's environment with the very large sustainability challenges we face as a global community. So what's needed to get to interoperability? First of all, is a consensus and understanding of the needs. So conferences like this one are very important. You going out and getting your colleagues excited about this is important. We need platform agnostic, machine actionable data and models. I'll talk a little bit more about this in the coming slides. We need semantics that can describe data and models and that AI can navigate to assemble data and models. And we need to pay attention to and reduce hidden costs. Again, some of these building blocks, the semantics are a language to describe scientific observations. The open and linked data need to be machine actionable, and there are a number of considerations listed here that we should follow for that. Similarly, with models, we need to have those be machine actionable, not just in public code repositories, but also have machines able to act on them and to have semantic annotations of their own. And we need to be able to define guardrails on when it's most appropriate to reuse a particular data set or model. So starting with the semantics, I'm encouraged by the fact that the four papers cited here, produced by independent groups, have come to a similar set of solutions for complex data interoperability across scientific disciplines. I think of a metaphor here of convergent evolution, where we have a common solution to a problem like flight across diverse groups of organisms, diverse groups of scientists producing similar solutions. It is to me a very good sign that we have a robust solution. And very briefly, I won't go into a lot of detail, but some of the key concepts here are that we ought to be using very small atomic concepts that we can build into more complex concepts rather than just making a very long list of the complex scientific phenomena that we want to describe. We need to distinguish between the phenomenon and the property being measured as well. So we're not just interested in the atmosphere, we're interested in the temperature or the pressure of the atmosphere. We need to measure the roles for some of these concepts where measurement occurs, atmospheric temperature, say, at 2 meters versus in the troposphere up higher. We need to account for different measurement methods, whether something is modeled or directly measured by an instrument and what type of instrument. We need to be able to look at not just ontologies for specific scientific domains, but at more general ontologies that can be paired with those that look at broader scientific measurement concepts. And we need to reuse existing semantic resources. Pivoting to models, we need to, I think, move from a world of which model is better or model beauty contests, some of which authors have done, including myself in the past. But I think this is a dated view. I think we need to think about the basic truism that all models are wrong and some are useful, and start thinking about when models are more and less wrong. So when we do that, we focus on Is a particular model more appropriate for a particular ecoregion, spatiotemporal scale, or when key data sets are or aren't available? And if we can, this is the guardrails I was speaking of previously. If we can focus on when models are best and most appropriate, and we can describe those guardrails, then AI can navigate that complexity, integrate the best available models, and we're not stuck with a single model that a modeler is most comfortable with and familiar with, but the best available models for complex and diverse scientific problems. Interoperability solutions have an important human dimension, and there's a technical dimension which I've been talking about today. The article and the interoperability strategy there on the left mostly deal with the technical problem. There's also these human dimensions of trust, user friendliness, equity, and community endorsement. And I really encourage you all to look at this blog post from 3 years ago, which I think is still quite relevant about these human dimensions of interoperability, which matter greatly. Looking at the technical side, this interoperability strategy, which our team wrote and published, focuses on SEEA, but the idea and the vision here, which we'd like others to get behind, ideally, if you agree with it, is that these accounts and indicators need to be rapidly recompilable. We need to be able to quickly produce them to extend new time trends as new data become available. We need to be able to do both very robust international comparisons, but also to enable countries to do high-level customization of their models. And at its core, to get this data into the hands of decision makers, the public, and the media as quickly as possible to be responsive to these modern sustainability challenges. So if this is a vision that you're interested in, I hope you'll read this, agree with us, and join us on this journey. What needs to change in order to do this? There are multiple entities that play a role in all of this, from funders to scientists, managers of data and code repositories, and practitioners. The field that you may be unfamiliar with is knowledge engineering here, which is called out, which is the people who work on the semantics and the tools to make these semantics easier to apply. And scientists and managers of data and code repositories should be familiar with knowledge engineering and working with them to enable the semantics that will enable semantic interoperability. Finally, this is my last slide here. I hope after today's talk and after this wonderful week of sessions, you'll be interested to continue learning more about interoperability and sharing it with your colleagues. To practice the best open science practices you can. This doesn't mean immediately jumping to the most complex open science practices, but starting small, using data and code repositories, making sure that you are using the best available metadata keywords or semantics. And then as time goes on, progressing to more advanced shared semantics and best practices for reusable and machine actionable data and models. Finally, finding someone in your organization who's really passionate about this and who can engage both your organization and the broader scientific community in this journey toward interoperability. Not everybody needs to be the expert, but we ought to be connecting our experts and setting some shared goals. So I hope after today's talk, you're excited to join us on this journey. We think it's an important and critical one, and thank you again for the opportunity to speak today.